Welcome to David Alexander Maths Tuition. This is chapter 11a on vectors. Okay, so what are vectors? Vectors are directed line segments. In other words, they are lines that have direction. So this line here starts here. If I call this point A and it finishes here, let's call that point B. So this vector, if it's going in this direction, starts at A and finishes at B. And I could call that vector the vector AB, with the letters AB and an arrow indicating that we're going from A to B. Now, of course, if the vector was reversed and it was going in the other direction, then this would be the vector that starts at B and finishes at A, so that would be the vector BA. Underneath we have another vector. If we say that this is the point C and this is the point D and we are going in this direction, and this is the vector C to D, and if we're going in the other direction, then it would be the vector D to C. Now, if we go back to, let's look at the vector AB, we can see that to go from A to B, we are going 1, 2 across, and then 1, 2, 3, 4 up. So the vector AB, that we can represent that in brackets like this, and as it's 2 to the right and 4 up, that would be the vector 2, 4. If we were doing the vector B to A, so how do we go from B to A? That would be 2 to the left and 4 down. So that would be -2, -4. In other words, because we are reversing vector AB, we could say that BA was the negative version of 2, 4, and we can expand out that vector, which would be, as I've already mentioned, -2, -4. To go from C to D, that is 1, 2, 3, 4, 5, 6, 7, 8, 8 across. So C to D, that would be the vector 8 because we're going to the right, and then 2 down because we're going down, that would be -2. And therefore the vector D to C would be the opposite. That would be -8, +2. Okay, let's look at these two vectors. I'm going to label this one vector A. So A, what is A? Well, it's 1, 2, 3, 4, 5, 6, 7, 8 across. So it's 8 across and 2 down. So 8, -2. Now this vector here is also 1, 2, 3, 4, 5, 6, 7, 8 across and 2 down. So this must also be vector A. So any line that goes from one point, 8 to the right and 2 down, can now be labelled as vector A. So it doesn't matter where the vectors are, as long as the lines are the same length and heading in the same direction, then it is the same vector. So let's take a quick look at the addition law for vectors. So if this is point A, this is point B, and this is point C. So we know that the vector A to B, let's say we know that that is called vector A, and the vector B to C is labelled imaginatively with vector B. How can I, so A to B is A, the vector B to C is B. So how do I represent the vector A to C? So this red line, well, how can I represent this in vector form? Well, to go from A to C, I can go A to B and then B to C. So what we're doing is we're just looking for pathways that are already labelled, and as long as we go from our start point to our finishing point over labelled routes, then we can now recreate a labelled route for A to C. So if A to C is the same as going from A to B plus B to C, admittedly going A to B and then B to C is a bit longer, but we do get from A to C, and we're taking labelled pathways. Therefore we can say that A to C is A to B, which is A, and B to C, which is B. So I can now give this vector or this line a label. A to C is now A plus B. Okay, so let's look at how we can do some subtraction with vectors. If this is point A and this is point B and this is point C, and vector A to B is A and vector A to C is C, then how can I label the vector B to C? So how can I go from B to C? Okay, well, B to C, I could go from B to C down the red line, but I don't know how to write that because this path doesn't have a name. But I can go from B to A and then A to C, and B to A has got a name and A to C has got a name. So B to C is B to A plus A to C. Okay, now b to a, we are going backwards down this vector a. So if a to b is the vector a, then b to a is the vector negative a. Plus a to c. Now a to c, we're following the vector in that correct direction. That's why it's really important to put these directional marks so that you know whether it's going to be positive a or negative a, by the way. And a to c is plus c. So therefore b to c is negative a plus c, although you'd probably write it as c take away a. So to go from b to c, we are taking vector c and we are subtracting vector a. So that is vector c minus a. Okay, so let's say that this line here is vector a. So vector a, that is 1, 2, 3, 4, 5 to the right, so I can write that as 5 and 2 up. Now, from this point here to this point here, that looks like a vector a as well because it's 5 along and 2 up. And from this point to this point, well, that is another vector a because it's another 5 along and 2 up. So therefore, this vector here is the vector 2a. Why? Because it's twice as long as vector a and it's heading in exactly the same direction. Now if a is 5, 2, then 2a, we can write that as it's 2 lots of 5, 2. Or we can say that 2a is just, well, double the numbers inside the brackets, which would be 10, 4. So it's handy to know that when you've got a number outside of the vector, a bit like expanding brackets, you can just multiply the contents of the brackets by that number. Okay, so here's another example using just some random shape that I've invented. So let's say we need to work out the vector a to c. So how do I go from a to c? I can't just beat a random path through no man's land here. I need to take labelled paths. So I know that a to c, I can get there by going a to b, by taking the vector a to b, and then taking the vector b to c. So a to b, so that is a, and b to c is b. So a to c is a plus b. Actually, there is another way I could have got from a to c, and that is going a to d, d to c. So that would be d plus c, or d plus c. And because we've started at a and ended up at c, then it doesn't really matter which route you take, they will be the same. So therefore a plus b will therefore equal d plus c. Not that that is massively important in this question, but it's worth bearing in mind that whatever route you take to go from one place to another, then it will still be the same in terms of the a's and b's or whatever letter they give you for the vectors. So if another way I could do a to c, I could go I could go a to e, e to a to d to c. I just added in other random routes, but as long as I'm not as long as I'm sticking to marked paths, then it's all going to work out the same in the end. Okay, how about let's say vector d to b. So to go from d to b, there's two options. I'm going backwards down the vector a to d, so that's going to be negative d, and then I'm taking a to b, so plus a. But I'd probably write that as a take away d, or of course I could do positive c minus b, or c take b. Okay, let's do one final one. Let's try e to c. So to go from e to c, it's just this short journey from here to here, but I can't just go cross country here. I need to take the established route. So to go from e to c, I'm going to go, first of all I have to go backwards down this down vector e, so that's going to be negative e, and then to go from there to c, I might as well go plus a plus b plus a plus b, and I'd probably write that as a plus b minus e. Of course I could go negative e plus d plus c, that would work as well. Anyway, so now we could label that vector a plus b take away e, or as I said, d plus c take away e. Okay, so here's an example of a geometric problem using vectors. So we know that ABCD is a trapezium. Now we need to be careful. We know how to draw a trapezium, hopefully. We know that it's got one pair of parallel sides, but you can't just draw a trapezium, just randomly label the corners or the points A, B, C, D without a bit of consideration. So the key thing here is that we know that the vector D to C is 3AB. So therefore AB and DC are parallel. So let's just say that this is A, this is B, and therefore this must be D, and this must be C. So I've just made it a bit longer because it does say it's 3 times as long. I don't think it is 3 times as long. It doesn't really matter. Also, I don't know if there's a right angle here or not. It's not going to matter. So A, B, C, D is my trapezium. So A to B, that is the vector A to D is the vector C, and DC is 3AB. Well, that means it is therefore 3A. And M is a point on BC such that B to M to C is 3 to 4. Okay, so what we need to think about that. So the point M is closer to B than it is to C. Now we've got a ratio here, 3 to 4, so that means it's 3/7 to 4/7. So B to M is 3/7 of the way down the line, BC, and M to C is 4/7 of that full line. So what we need to do first of all, and I'd do this even if the first question wasn't asking what is the vector BC, I'd be working out the vector BC so that I could work out the vector BM and MC. If I've got the vector BM written in there and the vector MC in it as well, then you can give me any combination of these letters and asking me to write it in vector form, and I've got it all covered. So first of all, the vector B to C has not been marked, but I can go from B to C by going B to A plus A to D plus D to C. So that is, we're going backwards down A, so that's negative A plus C plus 3A. So just cleaning that up, negative A plus 3A is positive 2A, so that is 2A plus C. Now, it's kind of difficult to write this on my diagram, because if I just randomly put an arrow here and put 2A plus C, well, that might be confusing because you might think that is the vector M to C. So I need to remember that B to C is 2A plus C. However, I can mark in B to M and M to C because I know that BM is 3/7 of the full vector and MC is 4/7. So what I can do is say that B to M, this is 3/7 of 2A plus C, and M to C, that is 4/7 of 2A plus C. I mean, you could expand the brackets and write that as 6/7 A plus 3/7 C if you wanted to. That's completely fine. So what is the vector AM? So to go from A to M, well, I'm going A to B plus B to M. So that is the vector AB plus the vector B to M. The vector A to B is A, and the vector B to M is 3/7 of 2A plus C. So that is A plus 3/7 times 2, which, as I said before, is 6/7 A plus 3/7 C. And a full A is 7/7. So 7/7 plus 6/7 is, oops, sorry, that should have been a C there, not an A, by the way. 7/7 plus 6/7 is 13/7. So 13/7 A plus 3/7 B. So that is the vector from A to M. So if I wanted to, I could just draw a line in and label that as 13/7A plus 3/7B. Okay, so this is a fairly straightforward problem. I just want to remind you that to show that two sides are parallel, that two vectors are parallel, they must be multiples of each other. So let's take a quick look at this. We know that CA is the vector A, CD, that is the vector 7B, and CB, this is A plus 5B. So to show that A, B and C, D are parallel, let's work out what is the vector to go from A to B. Well, we know that C to D is 7B. So to go from A to B, I can go A to C and then C to B. So I'm going backwards down A, so that is minus A, and then from C to B, plus A plus 5B, and negative A plus A, well, they'll cancel out. So therefore A to B is 5B. So they're parallel because one is a multiple of the other. And this, we don't need to think about, well, it might not be a multiple of 5, it doesn't really matter. They're both multiples of B, so therefore they are parallel.